This again. Ah, it's recording. Uh, Welcome to another exciting readings class. Today what I thought I would do is go over some of the homeworks, but first I have, to sort of give you a little bit of an overview of what I have planned for today. First of all, did anybody have trouble finding papers? No trouble? George, were you able to find 10 papers?
I found English relevant to Magna, and I'm still in they were pretty relevant,
Okay.
not, I mean, there's only a couple. It's not my idea to be out there.
Did you all have a chance to use the library to do interlibrary loans?
I was
Okay.
actually able to do
Okay.
at that time.
Did you have to join the digital library?
I did, yeah, I joined
We got a discount as a
I got a
student
discount.
member.
Right.
Yeah, I think you can actually sign up for as few as 6 months, and or you can go 1 month at a time.
So yeah, that helped.
Yeah. So if you're an IEEE student member, that's very helpful because you can gain access to IEEE papers. The membership for students is greatly discounted. How much is it, George? My God.
Yeah, it was very
I spend almost $300 a year.
yeah, it's a student discount.
So you got it for $18?
Something like that. Yeah.
I'm going to enroll in a course, maybe my own. I
No,
think
it
it's
was
not
very
ethical.
No,
Can I assign myself an A?
Yeah, it was very. It wasn't 18 or
It's unbelievable.
Yeah,
It's,
that's not for the professional.
I'm stunned. $18 and I'm paying. What a chump I've been. Why am I paying so much? I should just let you sign me up.
Yeah, well, I think it's true though that the one for the professional member pay a lot more.
Unbelievable.
Yeah.
So, one of the things that I thought would be interesting for us to do, we've already reviewed the America Invents Act. We had a nice little lecture about that. The America Invents Act is now in full force, right? Because it's what, the 19th? So it's been in full force for the last 3 days. It's a new day for everyone. Now it's first to file, so it's a rush to the patent office with many hastily written and poorly written patents for the how do we call it, patent examiner to review. Now, as it happens, and you may not know this, but graduates of the computer engineering program here at Fairfield University have been known to go work for the patent office. Sometimes very smart people work for the patent office. When Einstein couldn't get a job as a professor, he worked for the patent office. Sometimes smart people work for the patent office. So even if you're Einstein, you could end up working at the patent office. It's nothing wrong about that. And you get exposed to many interesting and wonderful ideas. You also get exposed to a lot of bad ideas. But at least they're different ideas. One of the things that I get involved with all the time is I get involved with people calling me up and telling me their ideas. And I don't sign a non-disclosure agreement. And sometimes the ideas are quite simple, and what happens is it's really a matter of execution. If you build a business and you have a product and you are on the market, you already have a competitive advantage relative to the business that doesn't have a product on the market. In this case, the fellow wanted to build a flow gauge for oil. Right? That sounds simple enough. People are always running out of oil, and it's just like any other flow gauge for oil with a difference. And the difference is it sends you an email when you're low on oil, and you can pick the number of gallons, and you can also see the graph of your oil usage as a function of time on your iPhone, and you can also compute when you're about to run out of oil. So it can give you, based on degree days, maybe plug into the weather and data mine information about how fast you use up your oil. Sometimes oil is used without cold weather because people use oil to heat water for showers and things. So oil usage can go on even during the summer. So this is kind of an interesting point. People don't want to run out of oil. In fact, they don't even want to run down to the bottom of the tank. And the reason why is because sometimes at the bottom of the tank there's sludge. And the sludge will clog the lines going to the oil burner motor. And then they have to blow the lines out, and it's a very expensive operation. So oil tanks that have been sitting for a great long period of time will often hold hundreds, if not thousands, of gallons, depending upon the size of the house or apartment building you're trying to heat. And oil companies try to compute how much oil is left based on your degree day usage. And they like to deliver perhaps more frequently than you would like. So he thought, well, wouldn't it be nice if you could just monitor oil usage? Simplest thing. No patent involved, right? You can't patent this idea. It's too obvious. So unless there's some design patent in there somewhere, a specific embodiment, in which case the patent may not have good value. How do I know if a patent has good value? Well, there's a couple of ways, but one of the things is what's the value of the product? Maybe the value of the market and the family of products, if it's a family of products. Sometimes people patent a basic design, like the design for this cup. If it's got a fancy full design, maybe that could be patented. It's not particularly fanciful, but it could be. Let's say it was the shape of George's head or something. I mean, it could be, well, maybe that's not good. The Wookiee mug. You could have a Wookiee, and it looks like a Wookiee, and then you could patent the design, general design of Wookiees, so that if you're a Star Wars person, it's not only trademarked, it's patented. A fanciful Wookiee mug, which you could use for cross-marketing to those 10-year-olds and or others who really enjoy Star Wars. I saw recently a Star Wars watch, and it was made by somebody who was just a fan, and they were selling it, and it was terribly expensive. So there are these things that people like to do with patents that go to design. There's other things you can do. Basic method design patents are different. There are utility patents, but they're different because they allow you to issue broad claims that cover anything that has to do with using your method for doing whatever. So I had a basic method patent for doing diffraction range finding. The diffraction range finders that were created that exploited diffraction range finding infringed on that patent. That's a basic method patent. So nobody was doing diffraction range finding before. Now anyone who does it for the next 20 years must pay royalties. That's basic method patent. A improvement patent would be if you use diffraction range finding with a specific kind of grating. We had one patent called the chirp grating. In the chirp grating, the number of rules changes as a function of your deflection across the grating. It's a variable pitch grating. So now that reads on the basic method patent. However, what it does is it allows you to get right up close without sacrificing accuracy to your target, and yet you can do it from that is, you can read right up close, but you can be from a far offset. So it gives you certain capabilities, like if you're digitizing the target, well, the workpiece is actually being milled. You can stop the mill and range into the target, and then proceed to do some more milling. And so oftentimes what happens is people take the workpiece off the mill and they put it on a coordinate measurement machine, figure out what to do, and then they put it back on the mill. This lets you do the ranging in situ. So there's an opportunity there for that patent, which you call the improvement patent. Now, is the improvement patent worth more than the basic method patent? In theory, no, because the improvement patent came with this idea that it was only for chirp gratings, and the basic method patent covered any diffraction range finding. But if you think about it, by the time the chirp grating came out and its patent, it was already 16 years after the basic method patent. So the time was running out on the basic method patent because patents are a wasting asset. And after 20 years, patents are worth nothing. What's going on out there? Are we having snow? It sounds like hail. Is it hail? So anyways, so both were utility patents, but one is referred to as a basic method patent and the other is referred to as a improvement patent. And one patent would cite the other patent. And so when the patent's got 4 years left, the value left in that patent may be rather less. And if the patent hasn't yielded good products that use the patent, then the patent may actually be worse than useless because the patent is just expensive and it's not giving you good return on your investment. Some people say you must have a utility patent in order to be able to raise good venture capital. And that may be true. Sometimes VCs really do look for patents. And if you've got a lot of money from a VC, they'll fund the patent for you, but they'll take a substantial assignment, usually more than 30%. Sometimes if it's not 30%, they won't even bother because it doesn't move the needle for them. And so I thought I would discuss this basic idea of who can apply for patents. Here in the new age, you don't have to be an inventor to apply for a patent. This is very weird, right? Why? Because now, if you work for a company, they can apply for the patent for you. You still get named, but because the patent has been wholly assigned to another party, if you're not interested in applying for a patent, doesn't matter, they'll apply for it for you. They won't ask you. You don't even have to continue working for the company. So they could fire you and still apply for the patent on your invention. Because presumably you signed some paper when you went to work for them. So when you go to these companies and you sign away your intellectual property, they take that assignment and then they say, thank you for your work, goodbye, you're fired. And then they take the work that you've done and your notebooks, which belong to the company, they apply for the patent. You say, you guys have been terrible to me, you're miserable. I don't want you to have the patent, I won't sign your papers. They say, we don't care because we can do it without you. Welcome to the new age of patent reform. Keep in mind, engineers are just interchangeable parts. And the only thing that seems to matter, it seems to me, are the corporations. So the corporations can go on forever now with their patents. Very interesting stuff. So this code has been in need of revision, I think. Application shall be made or authorized to be made by the inventor. No longer is this true. Welcome to the new age. Patent reform. And this idea that you have to do it jointly, I don't think this applies anymore either if you've got an assignment that already exists. This other thing, this oath, now needs to be revised. You don't have to take the oath if the corporation is applying. So how this applies now, I don't know. This is a whole new world, right? Patent reform. Used to be you had to say, this is my invention, I invented it. And you may not be the first to file, but you think you might be. And so then, this is an interesting point. What if you aren't the first to file? What about the prior patent that had been filed before you? Well, as it happens, if it emerges in the Federal Register, or if it comes out that it has been filed before you, it has priority, and then your patent is worthless. Now, suppose you and I both go to the patent office at the same time, and we both file, and you get a number, and I get a number, and your number precedes my number. Then you have the patent. It could be exactly the same time, but the numbers are always sequential, and one person's number will be before some other number. It just doesn't matter. Better file electronically and get the number in provisional patents count for establishing priority date. So it's a very interesting point. You don't have to do much to file a provisional patent online, especially when you're a small entity. Small entity fees have gone down quite a bit. I think they were $110. I'm not sure what they are now. Like 2 weeks ago they were $110. But here in the new age, maybe they're different. They could have changed. It's easy enough to find out. They were supposed to change. So this idea that you might have had the concept, let's think about this. Suppose you came to me and you said, gee, Professor Lyon, I had this idea that I was going to measure oil in my oil tank. Can you patent a basic method patent for measuring oil? What's patentable there? I'm just going to measure the gas gauges exist. People take a stick, they drop it in, they pull it out, they look. That's how much oil there is. Sometimes this oil tanks are perhaps small. 44 inches is a typical small oil tank. That's the height. And they might have it in your garage because it's not legal to bury them anymore. So, at least not in this state. I don't know about others. So now what you do is you drop in the ruler and you pull it out. You say, that's how much oil there is. What's the patent? But if you said, oh, but I use a computer and the web, and it sends me tweets, and it gets iPhone, and it has sensor, and okay, so what are you claiming? You can't just claim, oh, anything that measures oil. That's too broad. You can claim, how about the microcontroller system with a sensor that sends out email that measures oil? Can you claim that? And then, of course, you have to do the patent search and see if that's out there already. And if somebody has it already, then you say, well, geez, what else is there? So you could say, let's narrow down the claim a little bit so the patent, let's see what we can patent. So you say, oh, well, I'll take the claim and I'll change it to a sensor consisting of. Now you have to decide. Am I going to use a ribbon controller, a flexible resistor with a float, and if it floats at a different angle, I get different resistance? That seems simple. Or maybe I'll be fancy and I use a computer with ultrasonics, and I'll range down to the bottom of the level and come back. Maybe there's two ways to do it. Then one is what we call an embodiment alternative to the other. And if you decide, well, the cheap, easy way to do it is with a flexible resistor sensor with a float, you can say that is the preferred embodiment. That's what we intend to sell. But you could also build it with ultrasonic sensor. And so then you say to yourself, I don't know which I will use, because you haven't sold any product yet, because you don't have the patent yet. So you got to claim both. You got to put both in there. And so then you can start by saying, oh, I'm going to claim a microcontroller system that measures down to the level of the fluid, and I'm going to then have a claim that depends on the prior claim and say where that sensor is a flexible resistor. And then another claim that depends on the first claim, another dependent claim, where that sensor is an ultrasonic sensor. And then now you've got it covered. And you might say, let's get creative. Let's think of other kinds of sensors, where that sensor is laser ranging, LiDAR system. You could use LiDAR, why not? Could you use radar? Sure. Where the system is microwave, X-band or K-band radar system. Could you use something else to measure it? Get real creative, brainstorm everything you can think of. What other sensors could be used to measure the level down to the water? All the variations, you can put them into the claims, until there's so many claims that they start charging you and you run out of funds. But usually, claims used to be free. I think up to 20 it's like free. Maybe a little less now. I forget the number. So now I've got this idea, but the idea is just like, I've got the system, it measures oil. What about this other thing, the communication path? Is that a dependent or an independent claim? What if the communication path is Bluetooth Low Energy? BLE, Bluetooth Low, it could be. Where communication path is Bluetooth Low Energy. That's another, I'll call it, independent um, uh, claim relative to the claim that shows variations on sensors, but dependent on the primary claim where I have the big system that measures fluid levels. So now I've got Bluetooth Low Energy, but wait, how many different protocols are there for communication with a computer that are wireless? Oh my goodness. Right? There's Bluetooth, there's Wi-Fi, there's Zigbee, there's Z-Wave, there's XBee, there's all these different things I don't even know about. They could all be covered too. So I have preferred embodiment. Maybe I like the idea of communicating directly to my Android phone. I'll use Bluetooth. But Bluetooth doesn't go very far. And Bluetooth won't do the whole house, and Bluetooth won't send me an email. So I may need Wi-Fi as well. Yeah, I need Wi-Fi, and it has to get into an email server, and then it has to send me an email and say, maybe it sends the oil company an email. You can do a text message? How do you do that unless it reaches the phone? Unless you give it a GPS modem. You could give it a cell phone. Give the oil tank a monthly fee, and then he can set. He could call you on the phone. Hi, this is your oil tank. You have to feed me. I'm very hungry. There's something wrong with that, isn't it? Honey, your oil tank's on the phone. Take a message. I'm busy. Can he call you back? I'm enjoying this idea about the oil tank calling me on the phone. Suppose you are low on oil and it's 2 o'clock in the morning. Does the oil tank know not to call at 2 o'clock in the morning? I would be very angry with my oil tank. So, how do I know if I'm the inventor of this newfangled idea about the oil tank? What if the person who called me on the phone told me about their idea about measuring oil? And I say, oh, yeah. Then I think about it for a while and I say, you're all wrong. You don't want to use ultrasonic for this. You want to use flexible resistors. And besides, you'll never build anything anyway because you don't know what you're doing. Am I the inventor? No. I don't know. Am I? It says if I can build the product and take it to market, forgetting the ethical issues, which of course are profound for me because I happen to be the president of the Inventors Association of Connecticut, and I would never do that because it would harm the reputation of the organization. Because people tell me these things, and while I don't sign a non-disclosure agreement, they tell them to me in relative confidence. So now the question is, should I be building this thing? Should I be telling you even about it? Or should we be brainstorming about it? If they're never going to go for a patent, maybe there's a way we can help this person. We'll call it service learning. Come up with different ideas. What would be patentable if I was the kind of person who said, geez, it's a reasonable idea to measure oil, but I don't really know how to do it. What part of the invention am I claiming? Just the idea of measuring oil? That's not inventable, right? There's no patent there. But maybe there's something about the embodiment. And maybe there's something about sitting down and copywriting a printed circuit board. That's got intellectual property. Copywriting the software that goes in the microcontroller, that's got intellectual property. Maybe there's some element to the design of a cap that can house a microcontroller plus the battery and keep the whole thing safe, right? Because there's something about fuel oil. It burns, right? it creates flammable vapors. And the whole thing has to be done with relatively low voltage. I can't just plug it into 110 volts. So it's got to run for a real long time on a 10-year battery. There's something about this inventorship that, requires that we really think about the designs that make this non-obvious. And so that's the part, the design part, that I think you can really nail down with the patent. I get confused a lot of time by the basic concept idea. Somebody says to me, "Oh, I just want to measure the level of fluid in a tank." Is that the concept? There's more to it than that, right? So the basic idea of just measuring oil, that doesn't seem like one skilled in the art would have a challenge doing it. Because I take a stick, I put it in, I take it out, I take a look. That's measuring oil. People already do that. The thing that's different, making it, I'll call it a web-enabled oil tank, right? A networked embedded system for my oil tank. That doesn't sound like it's done now, right? So at some level, I think the concept has changed dramatically. And would anybody skilled in the art be able to build a web-enabled oil tank? I would hope that any graduate of the ECE Master's program would have a good chance of being able to execute on that design if they were hired to do it. I should think so. Are you required to explain how to build your web-enabled oil tank system in the patent? You are. You have to explain it so someone skilled in the art can build it. Now, you don't necessarily have to disclose all the code. You could use something like a flowchart, or a general pseudocode, or a general description of the algorithm, which doesn't sound particularly difficult to me. You don't have to put in all your microcontroller code. That's for sure. And you certainly don't have to put in all the wiring diagrams either. You could do a big block diagram. That's enough. Then there's this idea about a settled idea, a particular solution. This is the one that says, I'm going to use the flexible ribbon controller and or the ultrasonic system. That's like a very specific embodiment. That's not a general solution either. So let me think about this. Somebody has an idea. There's the Wright brothers example. We think it's a good idea to have an airplane that lets people fly. Can you patent that? I don't think so. Yeah, but if you have a detailed solution to the problem, maybe that is something that you could use as part of your patent. Now, it used to be you had to have more than just a concept, more than just an idea. You have to have some kind of a preferred embodiment, a solution to the problem. And that makes it patentable. So now suppose somebody works for you, and this is the tricky bit, right? And they make a contribution to this invention, maybe just one claim. They're a technician. They don't count. Are they inventors? He's a guy you hired, right? He came up with this idea. It helped a little bit with the patent, maybe just on one claim. He's a consultant, right? He's just a technician person. Is he an inventor? No? George? Depends. Raoul? What do you think? Depends. Why? What is it? You know, if there's a ruling, a court ruling that says a technician who made a contribution to one claim in a patent becomes a named inventor. So the number of inventors changes depending upon which patents are allowed. If that patent is divided up such that there are many claims and inventors lay ownership to individual claims, then the number of inventors will change depending upon which claims are permitted in the patent. So that's a remarkable thing, I think. What about this idea of keeping the lab notebook? Have we discussed that? Yeah. You number the pages, you write read and understood, and then you have somebody sign it and date it. You make sure that this is the kind of book where pages cannot be torn out. Right? That's very important. I personally use pages that have been sewn into a binder, and that's a proper notebook. The 3-ring binder is not a proper notebook because you can take pages out and put them in. I've had a joint inventorship before. My international patent on the chirp grading is a joint inventorship. Here's an interesting thing about entrepreneurship. It's very important to be careful about how you pick your partners. Oftentimes you're tempted to say, okay, we'll make it 50-50 because you want to be generous and you think the other person's going to work as hard as you. And then what happens is they don't work as hard as you, or they get distracted with other things, and then all of a sudden you've given away half your business. And also they have to agree with everything you want to do. When my joint inventor called me and told me to do certain things and I didn't want to agree without having a meeting, he wouldn't agree to a meeting. Interesting, right? And so we lost the patent collectively. And that's unfortunate because we couldn't come to an agreement. I said, "Why, come here, visit. Let's discuss it." Didn't want to do that. Okay. The patent wasn't worth that much, to be honest, but it had cost a great deal. This is six figures worth of expense to keep this patent going. What a shame. Patents get much more expensive as they get further down the line. So your first expenses with patents are not your last. So your lawyer fees, that's very high. $3.50 an hour is typical. But for just the patent office fees, they just keep escalating. When the patent first gets applied for, that's expensive. Then when it gets allowed, there's another expense. And then there are more expenses as it gets later in the life of the patent. And then if you have to translate the patent to different languages, and you have to go to different patent offices in different countries, it gets very expensive. So if you have an international patent, like I've got, $100,000, that kind of money, big money. So the decision to get a patent, yes, it's a legal decision, but first and foremost, in my view, it's a business decision. You have to decide whether or not this is something that's going to make back more than it costs. So far, my decision to get patents has been predicated completely on this idea that they're worthwhile in their provisional stage when you're seeking to raise money. But other than that, I haven't really found them to be worthwhile. Just me personally. There'll be another, I'll call it Inventors Association of Connecticut meeting coming up in Thursday next. I think that's the 28th. And we'll have Peter Propp from Connecticut from the Stanford Innovation Center come and he'll do a talk. And naturally, you all are invited. But what happens with that sort of thing? In fact, I'll bring it up for you just so you can see it. If you go to Inventus, see if we can get that. Isn't that terrible? Oh, so here's the next presentation. So that'll be on the 28th in the Dolan School of Business, and He's going to talk about, and I visited this place, the Stanford Innovation Center. And the Stanford Innovation Center is for startups. They have a very similar thing in New Haven. Only the one in Stanford is in a beautiful building that used to be the town hall. They completely redid it inside, and it has lovely big stone steps and what do they call these, Romanesque columns. It's a beautifully architected building, and they are also renting out space. So if you're starting a business that needs space, that might be a nice place to go. Me personally, my business never really needed space. I don't want space, and I don't like the idea of permanent employees either. All my employees have been freelancers so far. So, and I'm very happy for that. They're far away too. I sent an email, a package, little package, little tiny package, 2.3 ounces. They charge you for 3 ounces in this country when it's 2.3 ounces. And this little tiny package with a circuit board in it, I wanted to send to Bulgaria. 3-day Global International Express, 3-ounce package, smaller than the size of a pack of cigarettes, okay? $89. No kidding. So I says, well, that sounds a little expensive to me. I think I'll send it first class. How much is that? $9.75. That sounds better. How long will that take? I don't know. 6 weeks? Maybe more. Don't be in a hurry when you're sending things that far, right? Because you pay big money to get it there quick. The guy says, 6 weeks, I'll just build it myself. By the time it gets here, we'll be done with this project. So he wants to get paid, he wants to do the work, and he certainly doesn't want to wait 6 weeks for a circuit board. And who can blame him? So you got to keep it in mind when you're hiring people far away. On the other hand, in Bulgaria, the United States dollar is actually worth something. So that's very important. You can find, when you have a global economy, you can get good help for not so much money, I think. At least I hope he's good help. We'll see. I started from the beginning because I hit the wrong button. Okay, so we got the lab notebook part. Joint inventorship we talked about. This business about dividing up the assignment evenly, this goes to the question of, the business relationship you have with your partner, which is kind of beyond the scope of the talk today, but it's kind of so important. A lot of people select their partner because of proximity. This is one of those things where you say, well, I'll just partner with my friend. That's such a bad idea. How will your friend react when you say, you haven't been working very hard, therefore I need 60% of the company and you only need 40%? You think that discussion is going to go easily? How will your friend react if the business dissolves because you had a disagreement over business? Will you be able to stay friends? There are all these interesting and I'll say partnerships. Husband and wife teams, people have done this study. They don't do well when they do business together. Not a good idea. Just doing business with your friends, not a good idea. If you can find people who you've worked with in the past and you can do due diligence and see how things go when you work with them, that's much better. So picking your partners is a very important thing. You've got to be very careful about these sorts of things. And assignment, when you have an invention, it should be assigned to the company. So if you're going to create an invention and it's a joint inventorship, create a company and assign the invention to the company. That's key. So now it's the company's invention, even if it's a company that you are a founder on or a co-founder on. So assignment and inventorship are really very different things. And what will happen with the company is as the invention grows in value, the company will have stock, and that stock will have value. And that value for the stock will reflect the assets and liabilities that the company has. So you'll have certain things that you'll have to do, necessary business expenses. The ones that go on a regular basis, they'll be called OPEX, or your operating expenses. The ones that require you buy assets that you need to be able to retain, like machinery, like a drill press, or some kind of circuit board layout machine. Those are called CapEx, or capital expenses. And so then you start getting into this accounting thing, because with CapEx you have wasting assets that have to be depreciated over time. And so they are reduced. Like, for example, if I say, well, geez, I bought this book today and it was, an expenditure, and it cost me $200. I made up a number. Well, it was $200 in 2012, and now it's 2013, and there's a new edition. How much is it worth now? Nothing. Half, less than half, almost nothing. And so one could make the claim that this asset which I had put on the balance sheet now needs to be removed, or at least somehow depreciated. It's a wasting asset with a date and everything. Same thing for patents. Wasting assets. In a sense, that becomes a liability for the company, wasting assets. You have to deduct it from the balance sheet. So how do I know if I have a joint inventorship? This is so tricky. I think of it, well, I did this work, he did some work, I came up with these ideas, he didn't believe them, I proved the ideas to him, then he proved them to himself. I think I was the inventor. I don't even think it should be a joint inventorship. But good luck trying to explain that to a court, because you have to explain who thought of what when. And this is a very difficult problem. That's why I'll say the notebook is so important, but it's so rare that these things go to court and they actually look at the notebooks, and then there's so much expense going to court trying to prove these sorts of things, and then there's so much uncertainty surrounding court decisions. So I don't think of this as a particularly easy thing to do. All right, so I've chit-chatted long enough. Let's let the students talk a little bit. Has everybody uploaded their presentations? All right. Well, this may take a little time. Why don't we take a break? I think if this is going to sit here and give me the spinning beach ball of death, it's not productive. So we'll just let me just sort of stop it for now, or maybe I'll pause it. Welcome back, Chetan. If you're listening to this, if you think you're going to graduate this semester, don't forget to do your paperwork. You should definitely send me an email. I've sent you an email, and we in the office are all very worried about you. I hope he hears this. Oh my heavens! It's a 25-minute presentation? No. That is not possible. Well, let's see what Alfredo has to say for himself.
Active noise cancellation device by Alfredo Flores. Active noise control source. Loudspeakers used for active noise and talk will have a life of many years and they have to be clean and cool. Loudspeakers are available with aluminum or fiberglass foams with protection of the cool area from contaminants. At low frequencies and high sound levels, noise source volume velocities are large. When volume velocity exceeds the capability and available speakers, the number of speakers can be increased by placing them around the perimeter of a closed.
Okay, is this addressing the homework assignment? The homework assignment was supposed to be a list of papers, right? What are we looking at here? It's the PowerPoints that contain... I'm going to fast forward through this. This seems like an old presentation. Let's find the papers. Still looking for the papers. Still looking for the papers. Not finding papers. Okay, so now here's literature cited. Did this literature get cited? I got a list of papers, but at what point did he cite the literature? So there's no, I mean, I understand about sound. Sound is made of gas molecules. No, it isn't. Sound's a pressure wave. But so what? Where is the citation of papers? And here, this is without foundation or citation. Okay, let's see what's going on here. Here's a list of papers. Sound Engineering Explained. Are these journal articles? No. They look like books. So I've got a problem with this, right? Let's have a look at the assignment, because I think maybe we didn't understand the assignment. Ten prior papers, right? Not books. Papers. Why is the paper important? How is the paper different from prior work relative to yours? This is not a book about what sound is, right? It's a paper, a research paper. Use journal papers. It says that right here, right? So this assignment was not done. It was ignored or whatever they did. This is not what we asked for. Are we? Am I? Do you have a comment, or did I say something wrong? Am I too harsh? Okay. So I mean, let's think about this. These papers that you were supposed to cite in journal articles should have been listed here. But when I looked at it, there's like no papers. Yeah, this is completely devoid of any paper at all. So now let's assume that you're interested in finding papers on that would be acceptable. I mean, let's assume that's sort of. So you go to Google Scholar, and you do a search on active noise cancellation. And there's a ton of papers, 84,000 results. Now some of those papers will be IEEE papers. So here's 42,000 results. Some of those papers have full text, right? You can just download them and print them. So, you know, if you're having trouble finding papers, it can't be because of, you know, they aren't there. There are definitely papers. So this is kind of a problem here. Let's try somebody else. So I just stopped it. I think this that Alfredo, your assignment needs to be redone. It has to be about papers. You know, why is the paper important? Here's the superconducting dry ice motor. Let's see what we got here. Sarisha, you're up.
Good afternoon, everyone. Today I'm going to present the what are the papers I have read and what's their contribution to my idea. First of all, I look for superconducting material properties and superconducting materials paper which are available. This paper uh, based on superconducting materials that exhibit superconducting properties over 200 K, like high temperatures. This paper, like I'm going to use superconducting material in my project, in my dry ice superconducting motor. So I guess this one is related to uh, my idea. These superconducting materials results properties which are superconducting properties over 200 K, which is greater than dry ice temperature. So they in this paper they made like yttrium barium copper oxide composition. Like this one is combined of materials to exhibit superconducting properties. Other paper I cited, this one is superconducting homopolar inductor alternative for power applications. This is especially for power applications. So this system, it generates I mean it actually it's an engine that combines of rotor and stator homopolar.
Could you explain the word homopolar? What does that mean? Just in case anybody else doesn't.
A homopolar is like um, we have same pole, yeah.
Same pole. Does it mean the same pole or two poles that are similar to one another? Like homogeneous.
Right.
Versus heterogeneous. Because if
Yeah, I know.
you can have homogenized milk,
Right.
right? So it's all mixed up. Homopolar, does it mean that it's two poles that are similar orientation?
Yeah, we use same poles that are similar in rotor.
And so what would be the alternative to homopolar? Is there heteropolar?
I don't have an idea about heteropolar.
I don't really know about these things. I pretended to know, just in case someone else doesn't know, but in fact I really don't. So I have to ask you, because this is now your field. You have to tell us. So you now have a homework assignment. You must find out what is
Homopolar and
Yes.
related work, right?
And you have to come back and explain to us.
Okay. So this one is basically to used for ships to drive motors. This one also uses superconducting materials in their stator windings and in a field. To produce field, they use superconducting magnets. So this one is also I like. Some of these are related to my idea. That's why I did this one. Actually, professor, I found so many papers related to superconducting materials, but I didn't find any papers related to dry ice things. But I found, like, when I searched in Google and I looked for other websites, and I found like recently, not recently, I didn't remember the date. Someone, they did dry ice Stirling Stirling engine. Stirling engine that works on dry ice.
But are they just using the dry ice to create a pressure difference, or are they using the dry ice to create a superconducting motor?
No, they are not using superconducting motor.
Yeah,
Like
so your goal is not just to use the dry ice because it creates pressure
pressure, yeah,
differences or temperature differences. Your goal is to use the dry ice to get superconducting
properties.
dry ice temperature motors. So while Dylan has perhaps done a superconducting dry ice temperature motor, I should think that someone has used dry ice to create superconductors.
Yeah,
Because you can just buy that from like Edmund Science. It's a kit. So I think you should be able to. Can you create it? Can you create a motor that uses dry ice as the superconductor
I, I
temperature?
previously I read one article. They made a material which exhibits superconducting properties at dry ice temperatures.
Yeah, I mean that's certainly true. But the question is, what would it take to build a motor? Can you build a magnet that works with dry ice?
With that material, they already
Yeah,
prepared.
can you build a superconducting magnet that uses dry ice temperatures?
I should think about it because, like,
Well, if you can't build a magnet, I don't see how you're going to build a motor.
yeah, we need to build the magnet definitely to.
Let's start by building an electromagnet with superconducting windings that work at dry ice temperatures. If you can just do that,
We
then
can build
maybe you can build a motor.
motor. It's just regular thing that we can replace that superconducting magnet that we build in place of the.
Yeah, so let's build a superconducting magnet that works at dry ice temperatures. I think that's a good start. I think it's a necessary but insufficient condition for building a motor.
I'll have.
Does that make sense? I mean, how do you build an electric motor?
Yeah, if we have
that.
that.
Magnet and it attracts a thing, and then when the magnet turns off, the next magnet starts, right? So you need magnets, electromagnets.
That works at that dry air
Now
temperature.
you could use an electromagnet with a permanent magnet, and the permanent magnet could be a dry ice magnet. But I'm not sure how you do that. There must be a way to make permanent magnets that work only at dry ice temperatures. I think you need if you need a superconducting winding that works at dry ice temperatures, you should be able to build a magnet. An electromagnet.
So I found papers related to superconducting motors, and I didn't find any papers related to dry ice motors that
How
were.
about dry ice superconductors?
Dry ice superconductors, I found, like, I didn't find any papers. I found some work related to that. They did. I told you the superconductivity is possible at dry ice temperatures too.
But there's papers on this, right?
Yeah, I didn't find on U.S. patents and IEEE because
There's no patents.
no
But there's papers.
papers.
Okay.
So this one is also related to superconducting motors, and they build superconducting either generator or motor with hybrid. They use superconducting magnet in rotor and the other, I mean at least one permanent magnet. So the they use all they produce alternating current, and then the winding rotates like that. This one is also related to superconducting motors. As I told you, I found only superconducting magnetic motors. So this one is also this paper provides, like, at the initial phase, this at the startup phase they use induction, the motor runs in induction phase, and after that later on it works in synchronous phase. I- Induction phase, induced fields are related to torque shield, providing the coupling between stator and rotor during startup phase. After that, trap field comes by the superconducting conducting magnets. It couples stator and rotor windings. This paper related to aircraft launch systems. They use the superconducting magnetic motors, synchronous motors in aircraft launch systems. This motor is basically they didn't use with iron core in the motor, so it works with high temperature synchronous bulk magnets. This one, high temperature superconducting motors using yttrium, barium, copper, oxygen bulk magnets. They they uses this one at liquid nitrogen temperatures. So maybe we, by using this paper, we can use this paper and we can use that superconducting material that already built at driest temperatures to prepare a magnet, I guess.
Does the yttrium, barium, copper oxide magnet work at dry ice temperatures?
No,
Oh, so what magnets do work at dry ice temperatures?
it's it's a composite material of uh, I didn't remember that full length name. One two five
It's going
six.
to be in your papers then, right? Because you're going to have papers about magnets that work at
I
temperatures
didn't
of interest.
I didn't put that papers because you told you want patents that are available. That's why I have that list.
Yeah, I'd like to see journal papers that are related to your invention, even if there's no patent surrounding it, because it represents what I call prior art.
Okay.
So if it's been published, then it's prior art. So you cannot claim it because someone else has invented it.
Yeah, it's
So
their
if
work.
even if they didn't bother patenting it, um, publishing it certainly establishes their priority.
Okay, I'll do that one. So I thought like this we can use this concept and we can make superconducting magnet with this with at driest temperatures with that material we have at superconducting, I mean driest temperatures. It's 1256 by 1212 structure something. They they invented it.
Remind us again, what is the degrees in Kelvin for dry ice?
195K.
195. So it's 100 degrees Kelvin warmer than liquid nitrogen.
Liquid nitrogen. Yes.
Okay. That's very warm. Very.
This one is regular superconducting motor with superconducting winding and rotor, just rotor and superconducting magnet. This one is I found this one last, but I guess they use direct torque control algorithm. I didn't know direct control algorithm means. They prepared some equations. They said like they prepared some equations for direct control torque control algorithm, and they used it. But I don't have any idea about this exactly.
I don't know what direct torque control is.
When I look for it, like they prepared, like they invented some equations for direct torque control algorithm, direct torque control, and they used in that, but they didn't show any.
What is superconducting tape?
I told you I didn't find any information about this, but maybe I guess this one is related to my like maybe we can use direct
Does
or
this paper cite some other paper?
no, this one is not a paper, like they just this one is not a
This is paper 8.
yeah, I told you it's prayer work something related.
This is not a paper?
No, it's a paper, but they didn't show up the equations they used it.
But do they have other papers that they cited, a list of references?
I should look about it. This one is the
Yeah, obviously they're building on someone else's work, I should think. So it behooves you to find out what direct torque control is, I think, and what is superconducting tape.
Okay.
Can I use this tape to seal an envelope and send it to my accountant?
So I'll prepare that.
Because they don't sell it in Staples, right?
Yeah.
And that reminds me, if you find a place that I can go out and buy some dry ice temperature superconducting materials, you should send me an email about that, and I'll see if we can get some.
Okay.
There's a store near me that sells dry ice, and they put it in a bag, and I can take it to work, and maybe I'll put it in a little thermos, preserve it, and then we can run an experiment with
To prepare a magnet.
dry ice superconductor. So we should find some of these dry ice superconductors so that we can have fun with them. Don't you think?
Yeah, I
It
guess.
feels like science. Let's try and repeat some experiments and see what we can do with dry ice superconductors. I'm thinking I need like an ohm meter, and it should show me that there's like no ohm. And when I take the ice away, then there should be ohms. And I can say, aha, it's a superconductor. And it works at dry ice temperatures. And then when I know these things, I can say, great, we'll go out and buy some superconducting wire, and I'll wind it around a big nail, and then we'll throw it in the
Got
CO2, the
liquid,
ice,
liquid.
the liquid, and we'll monitor the temperature, and then we'll throw the battery on it, it'll pick up the paper clips, and then as it warms up, the paper clips will fall off. And we'll say, aha, we have a magnet. Discovery. And then we'll be able to go to business. Then don't forget Professor Lyon when you become a billionaire.
So I'll put that dry ice things also here.
Okay. I can't wait to drive to work using your new superconductor motor. It should be great fun, don't you think? I love this idea. Building a superconductor. That sounds like sustainable competitive advantage. You put Fairfield University on the map, and then you should give money to the school. They accept donations, you know. Let's see now. What do we got next? Yeah, I'm convinced all we have to do is run out to the store and buy some superconducting wire and throw it in the dry ice, and we have magnets. I feel like this would be a good Kickstarter project. People would like to buy a superconducting magnet. They would pay money for that. Real cash money. Okay. Sport the year.
Today I'm going to tell about the pre-year paper list, and this is the first one. And in this one we have a wireless power controlled outlet module. They explained about this, and they have 6 scalable modules into power outlet. The 6 scalable ones are the Bluetooth module, and a GSM module, and Ethernet module, and SD card module, and a power measuring module, and essential control module. They explained about each and everything. And in this one it controls and monitors the power consumption. which are plugged into our home appliances, and this is done easily. So in my project, I'm doing about the finding the power about each electronic device. So I think this is related to my work. So this is one paper among that. And the next one, this one is about the home automation protocols, not the on the top. This is about home automation protocols. In this one, they explained about all the protocols which we have for the automation, and we have X10, we have Smart House, and we have CBus. And they explained about each and everything. The Smart House, what are the advantages and what are the disadvantages of it, and the X10, how it is used in the home automation for the digital signals and everything. CBus, it's a consumer electronic bus. It is set of electrical standards and communication protocols for electronic devices to transmit data. And the X10, it's among communication among the electronic devices, and this is used for home automation. Right now, I'm doing in my project, after the power is measured at the outlet, those signals, they are sent to the main power supply. So I think we can use one of this to send the signals from one outlet to the main outlet. And path of a smart grid, at first I started about this project from a smart grid, like I read about smart grid and then about the smart meters, and then I read so many disadvantages about the smart meters, so I came to this idea about the outlets. So finding power at the outlets. So in this paper, it tells us exactly about the evolution of smart grid, how we need it, like the blackouts and everything, how we can reduce. Yeah.
In your citations, you should cite the paper properly. So use the little square brackets, put the author in there, and then at the end, I don't know, Srish, if you have a list of papers that you have cited, I can see that. Pat,
These are all.
you want to do proper lists of journal papers. So what I saw, yeah, a lot of patents, I didn't see any journal papers. So what we want to go for in this exercise is journal papers. So I'm thinking, after having seen some of these things, that we're probably going to have to repeat this. I mean, we'll go from, let's say, 10 to 20 journal papers, and we're going to have to make sure that we're citing things properly. Now here, I don't know which paper you're citing, and so I would put the citation in, probably in ACM format, with a little square bracket
Yeah, yeah, yeah.
author, and if you need more than one paper from the same author, put in A, B, C, or the date.
These are all the IEEE papers. So I have the citation with me. If you want,
Well, it should be in your slide as well.
yeah, I can send it again by tonight.
Well, it's all right. I mean, this is the first pass through, so we're probably
Okay.
going to be graded a little bit more easily this time. But next time, we're going to want to see proper citations.
Okay.
And we're going to want to see a list of journal papers.
Yeah.
So we'll write that up for perhaps I'll call it homework 9.
Okay.
It's 9. So it'll be 9 next week.
Okay. And this one, it's the development of smart power meter for AMI based on Zigbee communication. In this one, AMI is the advanced metering infrastructure, and we can use wireless communication for it. And this one, this helps in Zigbee based smart meter. A Zigbee system is then designed and integrated into the proposed power meter and use it to detail power consumption data. And we can note down all the results at the rear end processing system. And while in my project, after collecting the data, we can use the Zigbee communication also to transmit data to the same place, the main cable. And this is one more thing, estimation total power consumption by servers. In this paper, they told us about the power consumption. We can estimate the power consumption by servers, like in the data centers and everything. And it is difficult to calculate because each server can have different ROMs and everything, and they are linked to so many things. So in this paper, they told us how to calculate the aggregate power of the in data centers. So in my thing, we are calculating the aggregate of the power, but not in the data centers, just adding the whole thing from different outlets and using it. To find out the total power consumption of the house, we add the power of all the outlets. Yes.
So do we have the list of papers after this?
These are the papers, but I didn't write down all the citations and everything. But these are the paper names and everything. I'm just telling you what this paper is about and how it is related to my project.
So, if you were going to apply for a patent, what would your invention be? Where is your contribution to the field?
Like finding the power of the outlets. That is not done yet.
Yeah, people already can do that. So you can't really claim it on a patent. Right? It's kind of like I can find the level of the oil. I take the stick.
No, we can find.
I take it out. There's the level. Right?
We can connect the electrical device to an outlet, and then we can note down all the readings of how much it is using, the power consumption for each and
Kilowatt device do that already?
yeah, but it don't give us continuous readings, and it won't give us all the readings. We have to just note down each and everything.
So your contribution is that you develop a computer system that does it.
Yeah, like everything is noted down, and we'll know how much power you're using daily and how much each electronic device is using.
So is it your claim then that nobody has a smart outlet retrofit for a whole house so that a computer can monitor every outlet?
I read so many things, but till now, no.
No.
They have different things. I wrote down those also. Like this one gives us an existing. These are all the existing power outlets. This one and this one. This is a kilowatt, and this one measure power from an appliance from a wall plug outlet.
I have kilowatt.
You have yeah.
I have one, and I used it just to sort of look and see what my server was pulling because it's on
Yeah.
all the time.
So these are some of the
But
products.
kilowatt is not network. Kilowatt is just you have to go up to the outlet and you have to look at.
Exactly, we have to write down each and everything to note down the power. We have to go there and we have to do everything. Instead of that, we can just give them a digital signal so that it will automatically note down the usage of the device in the whole house and how much we are using exactly of each and every device.
POPs technology. What does that stand for?
Per outlet power sensing.
Hours.
Yeah, this one they are using it in data centers. This is mainly used for servers, so that in so many computers are connected to it, so that they can find out the.
Look what you've done.
I think you have to enter your password again.
I think this should be reflected on your brain.
Oh, I.
What happened here? This is your notes?
Yeah.
Here.
I have so many papers, so I don't want to get confused.
Why am I locked out in the middle? Yeah, very interesting. So, is this still recording? Yes, okay. So this is the end?
That is the end.
Oh,
I just
okay.
wanted to tell about the products and how it is different. That's all.
All right. So I mean, I looked at it. I think it's very nice, but let's try and keep in mind what it is we need to do for our next time. You're going to need to have something like you know, the author. Make up a name. Schmo, comma J. That could be a Jane or a Joe. So it's an equal opportunity Schmo. And then it could be J Schmo from 99, which probably means 1999, as opposed to 1899 or 2099. Or if you're really not sure and you want to be year 2000 compliant with all of your references, you might say something like, you know, J. Schmo 1999. And then at the end, I would like to see a full citation so that I can go and read the Schmo literature and see if Schmo has some patents. He's always been a Schmo, and he's come from a long line of Schmoes. So that's something that we should know. We need to know about Schmo.
We have to mention about the volume and issue also, right?
Yeah, if you're going to do a proper citation, I give you, I believe, a guide. So when you go to courseware, thesis work, and you look, you've got this sort of follow these directions for a technical paper. And that's kind of what you're doing, right? You're writing a technical paper. And so then I have these directions. And when you follow these directions, you'll have literature cited in the following way. So now the way in which it's cited in the paper, Aho et al., because there are too many authors, you don't list them all, so et al. Is an abbreviation for a Latin expression which means et ali, so that means and others. And then what you would do is you would spell out the others, right, because you don't want to put all those people in here because it would clutter up your narrative. And then in theory you'd like to put the date in because that helps you to locate the publication. And because it's a title of a book, I italicize it. If it were the title of a conference, I might italicize that instead and put the title of the paper in quotes. You know, there are all kinds of styles that you can use for these things. Anyway, that's what I like to use. It's an ACM style. So here it says Strunk in white. And so presumably Strunk in white is here. But the only way that you would find it is because somebody said, look, I cited this thing that says omit needless words, omit needless words, omit needless words. And that comes right out of Strunk in white. So it's clear I didn't make that up. And it's also clear that if I want to, I can go and read the Strunk in white book. So my literature cited should actually be a series of elements which have been actually cited. So when we saw Alfredo's work, we saw a whole series of statements about sound, but no actual literature had been cited. Further, the literature that you must cite should be journal articles. Okay, it's not patents. Okay, it's not conference papers. Journal articles. So we now know how to find journal articles using Google Scholar, and that's something I think that we should be focused on. So for next time, we're going to double the number of papers that we cite, and we're going to cite them properly, and we're going to list them. So there'll be 20 papers. It's a readings course. That means you have to start reading. It's for sure, right? Let's make sure there's some reading going on here in the readings course. And there must be learning too. Don't forget learning. So if somebody says homopolar and you don't know what it is, then you didn't learn about it. So then you must tell us. And so then we can have learning. Because we need to learn too. It can't just be for you. It's not fair. So there, in addition to learning, there could be teaching. So now is your opportunity to teach us about homopolar. Alright, let's see what Chitan has for us today. Oh, this looks very interesting. Maximum power point tracking. There is no audio here. Is Chitan snowed in? Chitan, I'm not going to do this for you because I don't see any cited papers. Oh, yes? Well, it has to be uploaded to the Axiom system. Well, I don't know about the email, but I don't see any audio, and I don't see any papers. Unless this is a paper. Yeah, maybe papers. No list of papers. So it looks like somebody wrote something, we don't know who, and they published it somewhere, but we don't know where. You can see how dissatisfactory this is. This is a very unsatisfactory citation. Someone wrote about logic, and apparently the logic is fuzzy. And we don't know what that is, because we never used fuzzy logic before for anything. Right? I didn't study fuzzy logic when I was an undergraduate, although I did learn about it when I was in graduate school. So if someone is going to talk about fuzzy logic, they better tell us what that is, because most of us will not know, I think. Does anybody here have any experience using fuzzy logic? Oh, I kind of know about it a little bit, but I never used it for anything. Has anyone here ever used or built an expert system? No. Okay. How about an inference engine? No, what are those things? Okay, these are very interesting things. They're not what we normally teach in a readings course. Fuzzy logic is like a whole other lecture. And fuzzy controllers that use fuzzy logic are basically using rules that consist of trapezoidal probability distribution functions that can be created with corner points. You can create the trapezoids so that they have start and end points, and then they have sustain points, and usually you define a trapezoidal function with 4 points. And then you can overlap it with other trapezoidal functions, and these things are supposed to associate memberships in sets. And you can use them for control, the same way you would use what's called an expert system. You create what's known as rules of thumb, or heuristics, for establishing where the fuzzy control points should be. So, for example, there was a fuzzy controller for a pancreas, which puts insulin into the blood. And so its goal was to try and stop somebody from having what's known as insulin shock, or going into a coma from insufficient sugar. You have to have the correct amount of insulin in the blood. So the fuzzy controller for the artificial pancreas said, look, if they're going into a coma, they need sugar right away because they're having a sugar deficiency. They go into an attack which is known as hypoglycemia. If you're a diabetic and you don't take your insulin properly, and you go into the diner and you have a Coke and a burger, this Coke has sugar, the burger has proteins, it gets into your system, and you're unable to metabolize the sugar. The improper amount of sugar causes the sugar level to go up way up high, and so you get a sugar high. And then if the insulin kicks in improperly, you can become hypoglycemic and you have a way depressed amount of sugar, and you can go into a coma. It's a very dangerous situation. So this fuzzy logic says there are certain rules doctors use when you have an insufficient amount of sugar, and they find ways in which to introduce sugar into the bloodstream. You know, sometimes you can stop it by having a candy bar. You know, somebody who's in this situation and is having wild swings in their sugar levels knows kind of what to do in order to get themselves out of this problem, this situation that they're getting into. So you try and put those rules into the fuzzy controller. You know, if the sugar goes up this much, then you put in only that much insulin. If it goes up that much, then you put in way more. So there are all these different rules you can use, and you try and encode them into the controller. The hybrid controller uses both the rules from the fuzzy controller and rules from a regular controller, and they have regulators, linear quadratic regulators that you can impose upon a system that can measure things continuously in order to keep fluctuations within a certain level. So the system that I had become familiar with came from a fellow who was doing a PhD thesis that resulted in an artificial pancreas. And they used fuzzy controller and a linear controller. So it wasn't my thesis, but I knew about these things. Did Chitan tell you he wasn't going to be able to make it today? Is there maybe some other thing that he uploaded? Well, I guess we've already looked, so we'll go on. George, you're up.
Alright, this afternoon I will be talking about some of the papers I read over the break. The 10 which I read. Okay, this is the first paper, and before I start, I also made the mistake of not properly citing my papers at the end, so bear with me. So the first paper, and I also another thing, the prior art thing I kind of messed up on. I don't think I understood fully what I had to do with it. So we'll talk about that, I guess. All right. So for the first paper I read, it was titled "Magnetic Levitation Technology for Automated Guideway Transit Applications," and this paper basically discusses the primary application of magnetic levitation, upon which that's my project. You know, basically the force field repulsion of meteorites and asteroids. So it's based upon magnetic levitation. This paper talks about the requirements for various magnetic levitation applications and mentions such projects in Europe, the U.S., and Japan. This is important to my idea, because my ideas, like these ideas, are I didn't mention them, but is an application of the maglev technology, in which basically magnetic they repel magnetic levitation is basically how my idea repels, how my project how it repels using magnetic fields. And trains use this all the time on maglev trains. The second paper I read was a basic overview of maglev train technologies. It summarizes train technologies from the perspective of an electrical engineer. It helps clarify maglev train technologies at a glance. It is important to my idea because of all the different maglev applications, mine shares the most in common with the trains, and so I guess the prior art of this paper, that's why I would choose it for. It would have a lot in common with my idea. Okay. Paper 3. Oh, by the way, all of these papers I found because I joined the IEEE, and actually it was very helpful to look on their database, their digital library. So that was very helpful, I found. So I suggest, if you want to find a lot of good papers on it, if you subscribe to the IEEE. So on the output power index of magnetic levitation, power supply for maglev train. This paper is about a certain type of, it's called a magnetic levitation power supply, MLPS, for maglev train, and it's important to mind because similarly I would need a way to power my the system, the maglev system on board, and this would be a good example to use and possibly serve as a basis. And like I said, I kind of messed up with the second part of the prior art, so I guess we'll have to redo that in my next paper, the next homework. Paper 4 is titled "The Analysis of the Combined Maglev Levitation, Propulsion, and Guidance System," and this paper is a particular analysis of a Japanese maglev system that uses only one set of coils. That is, talk about coils, that means magnetic coils with the combined levitation, propulsion, and guidance functions. This could be a good prototype for the proposed system in the aircraft. Paper number 5 is titled "Magnetic Levitation Technology of Tracked Vehicles, Presents Status and Prospects." So this paper discusses there are about 5 different types of magnetically levitated vehicles. We haven't the only vehicle we've really focused on so far is the train. The most popular of which is it uses technology called electrodynamic levitation, which uses superconducting magnets, which you may know something about from Sarisha's project. It's important to mind because, well, I didn't mention it, but superconducting magnets make the process much more efficient, and they're compared to the regular magnets, and there's less heat loss, and it's overall more efficient. Sorry, that got cut out there. Requirements for an electromagnetic system of superconducting levitation. It goes on, but I didn't have space for it, so I just. I think they're relatively hot. They would probably, in my case, they would use liquid nitrogen because just for. That's considered colder. Oh, I'm maybe I should have made that. Sorry. They're not the same. Okay, well, forget that I made that comment. So yes, they do. To answer this question, they would use liquid nitrogen because these temperatures machines operate at very high temperatures. Okay, so for it was on paper 6. What did I say, paper 5? I'm sorry, paper 5 was about, it talks about the different types of, it doesn't necessarily focus on superconducting magnets, although that's one of the things that's in the electrodynamic levitation, and because these things are important to my work because they cover the improvements and advancements to the maglev technology, and which would make the system overall more efficient. So it's important to focus on these things. And so paper 6 is actually about the superconducting magnets, and once again, they're more efficient and more powerful than the regular magnets. And will make an overall big difference in the overall design. It's important, and that's why it's important to my work, because they would make the system overall efficient and operate at a work better overall. Paper 7, it's something called Supervisory Particle Swarm Optimization Control Design for Maglev Transportation System, and that's a mouthful, but it's basically a online control for magnetic levitation system. Well, it would be important to mind because it would serve as a good basis example because if I were to have build my system, I would need means of controlling it, and so that could serve as a basis for.
Could you explain, is the particle swearing or is it swarming?
It's sworn. It was on the paper. I was
Sworn.
sworn. SW, like a bee swarm. Like I didn't.
Swarm. They don't swarm.
That's what I didn't.
That's what he wrote?
That's
He
what
wrote
was written.
swarm?
That was written on the paper.
Oh.
I'm not.
He doesn't mean like a bee swarm.
I actually don't know what is meant by that.
I see.
Um.
Well, I mean, when I think of swarming,
Yeah,
I
you.
think it's SWARM.
Right. No, that's what was written on the paper. I assure you.
Were they from the United States? Were they English speaking?
Actually, they may have been from Japan.
So
A lot of
so
this.
English was their second language.
I mean, they came from. It could have. This paper could have come from Japanese researchers.
Gotcha. Okay.
So it may be misspelled. I don't know. Okay. Paper number 8 is about. It's titled "Pulse Linear Induction Motors in Maglev Applications." This is a lesser known type of linear propulsion, like going in a forward direction, compared to the you hear more about the regular linear induction and synchronous motors. This is important to my paper or my work because all maglev systems, regardless, need one of these motors. If linear propulsion is to be achieved, so it's useful to know about how these things work, how the motors work. And actually, the pulse linear induction motor is advantageous over these because it has better power factor. So that's something that I didn't mention here, but remember reading from the paper.
In a pulse linear induction motor,
Yes.
how fast do the pulses come?
That I did not. I read about, but I forgot. It's in the paper somewhere. 9 is about. The title is Investigation of the Stability of AC Repulsive Force Levitation Systems for Low Speed Maglev. This paper talks about the stability of the repulsive force AC induction levitation system, focusing primarily on the secondary conductor. It's important for my work because in order to hypothetically repel the asteroids and other bodies, celestial bodies, you need some sort of repulsive force, and this provides an example of that force, but at a low speed. You would sacrifice the repulsive force for the low speed of the system. And then finally, the last paper, paper 10, is a type of control strategy that uses it's model free, and it's titled Model Free Control Design for Hybrid Magnetic Levitation System. And I believe one of the 3 different strategies make up the hybrid maglev system. They include a simple proportional integral differential scheme, a fuzzy neural network, which you talked about a few minutes ago, FNN, and a robust control for hybrid maglev system. The model free, what I drew from this that I liked, I liked the fact that it was model free seems to be more simple than other control strategies you could choose, and could serve as a prototype example for the spacecraft maglev system. So I like the fact that it was model free.
What do you exactly
It would be the I found this paper. It would be the overall system, the maglev system, for the
You can just turn it on and off with a switch.
well.
Here comes an asteroid.
I mean, it's not that simple. It would have to be. I mean, I read about it, and apparently it's not. You can't just like have it on and off. It's more complicated than that. It's way more complicated than that. I mean, all the other technology, like the
Well, this is magnetic levitation, but all you really wanted to do was keep things away. So you're doing magnetic propulsion. So if you turn the
Right.
field on,
right.
you know, it's not like you have to keep it stable. You can just turn it on full force and propel all the goodies.
Yeah, I guess. Maybe I'm making it too complicated. I don't know.
What do you maybe with a magnetic levitation system, you're trying to control the distance of the levitation based on the magnetic forces involved.
Right.
That's not the same thing as what you're doing. You're doing a force field, so you
Force
just want to
field.
turn on the force field.
Yeah, but I thought I'm pretty sure the force field was like was the fact that magnetic levitation is being used as a force field. The technology. Maybe I don't.
Are
Maybe.
you really levitating anything, or are you just generating a magnetic force field to keep things away?
Well, maybe it's more of a force field, but maybe I have to.
I mean, I can understand if you say, I
Right.
get a certain amount of force to lift this cup,
Sure.
and that's a different amount of force than when, let's say, somebody like me steps on the cup.
Right.
Then I have to adjust and I have to control the force to make sure I don't make the cup go like this. So I
Right.
have to go like step on the cup and it goes ooh, it keeps me the same distance away, so there's control.
Right.
So if you just said, here comes the cup, turn on your force field to go boing and pop it away. You don't care how much force you use as long as the cup doesn't get there.
I guess. Yeah. So maybe I don't know.
Unless you were trying to adjust the force field to only give enough force to keep the cup away. But
Well, I
I'm
think it
not
has to
sure.
be a range of force because I guess they're all
You
different.
can't just use force? Say what?
Maybe not. I don't know. I don't think so.
Alright, well, I'm pretty sure whatever control system you have for levitation is going to be different than the control system you use for propulsion.
Could be. Yeah.
What else you got? That's it, paper 10.
That's it. Yeah, and I don't.
No list of papers.
Those are all the names, the titles I gave. I didn't do it properly.
At the end.
Yeah, I didn't list the reference. Okay. So I'm sorry for that.
That's all right.
Okay. So, any questions? Comments? Okay.
Okay.
Good afternoon, everyone. Before starting the presentation, I would like to say that there is a small change in the topic. So previously it was like the vitricity for microcontrollers especially, but Professor Douglas sir suggested me that this should be like a very narrow kind of research. You need to be in a broader way. So I came up with this. The new idea is the vitricity using the fractal antennas. So the first paper which caught my eye was the vitricity, not so original at all after all. So this was an experiment connected by using the Tesla's principles and all those things, using the induction coupling principle to transfer the electricity wirelessly, but it's just over only a limited distance. So the transfer of electricity was cannot be done for a very long range. So there was a drawback, sorry. drawback. And the second paper was this goodbye wires. There was this team in MIT and a group of electrical engineers who um, who made a live example using the vitricity concept. They powered up an 60-watt bulb with a range of 2 meters. So the efficiency was fine, but even though the efficiency was good, but still there are some electronic losses while when the electricity was transferred wirelessly from one place to another place. So this is one of the application, and also it's a paper, wireless energy transfer for refrigerators. These people come up with some improved configurations to power up the refrigerators using the wireless using the vitricity concept. And so previously, as I was saying, that there were some losses. This paper, this wireless energy transfer using magnetic materials to shape field and reduce loss. So in this paper they clearly mentioned that by reshaping the resonators, the source and the destination resonators, we can get a better efficiency with reduced loss. So this is what the vitricity concept covers of. But and this comes the fractal antenna, a novel antenna miniaturizing technique and applications. So this fractal antenna is a special kind of antenna which has this which uses a fractal self-similar design to maximize the length or increase the perimeter to transmit the electromagnetic radiation. So with the guidance of Professor Douglas Lyon, I thought of increasing the distance or the range of the electricity concept using the fractal antennas. Like the transmission of the electricity will be done for a longer range using the fractal antennas rather than using the copper coils, which the Tesla explains, which the Tesla techniques explains. So there comes an iterative model for fractal antenna. There has been some experiments done using these fractal antennas. So in those experiments, the thing which has been proved was that the experimental and numerical methods show a self-similarity property that it can translate. It can transfer the electromagnetic behavior. So I think this can be used for the vitricity concept to transfer the power wirelessly. And also there is a frequency independent feature in this fractal antenna, which we can which may be like a major advantage for the vitricity to power up the any kind of devices which operate in a different kinds of frequencies. But the main issue is that the vitricity actually operates in the radio frequency, which is from 3 kilohertz to 300 gigahertz, but these fractal antennas mostly operate from 160 megahertz to 6 gigahertz. So
Is that for transmitting power, or is that for transmitting in general?
transmitting in general. And again, there is this paper, the fractal antenna applications in wireless telecommunications. So reading this paper, I thought I came up with this conclusion that these fractal antennas can be used for wireless telecommunications. Then maybe these can be even used for transmitting power also. So the main advantage of this fractal antenna is that it does not need any additional loading components. It is cheap and cost effective. So this might be a better way to transmit the power wirelessly using the same vitricity concept, but not the copper coils which we have been using previously. So And then next paper is the effectiveness of space filling fractal geometry in lowering resonant frequencies. This resonant frequency is for every device. When we use a capacitor and a resistor, there comes a resonance frequency. It means that both the antennas from where the power is transmitted are in a resonance, are in the same phase, are operating in the same frequency. So it's almost similar to that of the Vitricity concept, where the power has been transferred wirelessly. But in that case, we use the copper coils, as I told before. And the next paper is an overview of the fractal antenna engineering research. This research has been primarily focused on two areas. First one with the analysis, and the second concerns on the application of the fractal concepts to the design of antenna array. This paper is not completely related to the Vitricity concept, but why I cited this paper is that we need to know what the fractal antennas actually deals with, how it works, how it operates in different kind of frequencies, and so how it works. So that's the reason I cited this paper, so that we can use it in the Vitricity. That's it.
So, have people used different kinds of fractals to build different kinds of antennas?
No, it's the fractal antenna itself is like a different kind of antenna from when compared to the regular antenna.
How many different kinds of fractals are there?
Fractal is like a small part of an equipment or something like that.
Correct answer to my question is an infinite number. Fractals represent any curve that
Or geometry figure that resemble the similar frequencies.
define a fractal.
It's like the smallest part which which has the same and similar characteristics of that of the parent, something like that.
Does anyone know how to define a fractal? A fractal is a curve whose topological dimension is strictly exceeded by its Hausdorff-Bessel-Kovic dimension. Do you know what a topological dimension is? No. Do you know what a Hausdorff-Bessel-Kovic dimension is? No. Okay.
But
The way you measure the Hausdorff-Bessel-Kovic dimension of a curve is you build a Minkowski sausage, and you do it by taking circles and encapsulating the curve and touching the circles to one another, circles of a specific diameter, and then you run the circles along the curve and count the total number of circles, and that is the length of the curve using a circle of a specific diameter. Then you change the diameter and you repeat the experiment. And you change the diameter again and repeat the experiment. And you plot the length of the curve as a function of the diameter, and you get the slope of the curve, and the slope of the curve, 1 minus the slope, is equal to d sub h, the Hausdorff-Bessel-Kovic dimension. If the curve is just a single line with squiggles, then it is said to have a topological dimension of 1. So then what you want is a Hausdorff-Bessel-Kovic dimension which strictly exceeds the topological dimension. And this is how you define a fractal.
so
The number of different fractals is infinite.
okay.
So you can have a Sierpinski carpet, you can have a Koch curve, you can have any one of a number of different antennas, all of which are fractal antennas. And so then the question is, how do you know which fractal antennas to use? I don't know if anyone knows the answers to these questions, but certainly you want to start by being able to identify
Maybe with depending on the frequency ranges of the antennas. I mean, it actually.
Let me see if I can do something with the computer here. Oh, why don't you take this thingy? Thank you. So, the Hausdorff Besicovitch dimension of a fractal is, did I spell Besicovitch wrong? There's probably more than one way. It's not English, you know. Yeah, so it's not a statistical dimension, it's a topological dimension. And you can see there are the circles, and when you change the number of circles, the coastline is different. And so what you're looking for is a way in which to measure the length of a curve using different length rulers, effectively. And as the rulers get smaller, the curve appears to get larger. So if you want to measure the coastline of Britain, which was the original exercise, if you measure it with rulers that are a mile long, you get a different coastline length than if you measure it with rulers that are a foot long. And the rate at which the length changes is a function of the diameter of the radius d ball that's used to capture that curve is going to allow you to do the computation of the Hausdorff-Besicovitch dimension. Let's see, do they show you a picture? When you take the circles away and you just show the outline of the circles, that's what makes the Minkowski sausage. And they don't show you the computation. List of fractals by dimension. Lots of different fractals. And so now you can see tons of different fractals. Hopefully. Many different fractals. All different shapes. So, for example, here's this quadratic cross. You can see by changing the depth of iteration, you can get many different subparts. Right? So it gets deeper and deeper, but they all look self-similar. But self-similarity is just one artifact. If you wanted to look at the mathematical definition of what makes a fractal, that's when you get into the Hausdorff-Besicovitch dimension. So here's an interesting looking antenna. A completely different one than the cross. Is this one better for wetricity? Well, we better run an experiment and find out. Certainly, this one is different. Sure. I mean, you could tell me that this works good for wetricity, but only if it is 2 gigahertz wetricity. Maybe it works really badly for 60 hertz wetricity. Yeah, maybe there's good applications for that. Maybe the depth with which you do the fractal changes things somewhat. There's an interesting looking antenna. I like this one, the hexaflake. That looks like it might be a good antenna. But I can't tell by looking if the hexaflake is better than, let's say, this one, monkey tree, because it looks like monkeys, I guess. I don't know. That's a Julius set, what some people call Mandelbrot set. Here's the Wunderlich curves. Oh, I like that idea. Oh, they need their own page. They don't have one. Let's see. So, lots of different fractals here. All constitute, like, that's a good one. I like this. You can take a, they call it the Minger sponge. If you take a Sierpinski carpet, you can do it in 3D and make a Sierpinski sponge. see what else we got. Oh, look, cauliflower. It's a fractal. Actually, that's a 3D fractal.
And also it depends on the distance of how much the range it is.
Broccoli. The broccoli fractal. Brains. Zombies eat them. But I only know this because television. Let's see. So, I think there are... I'll put it a different way. There's no limit to the number of fractals. Probably there's a limit to the number that have been published. And certainly the number that is being published is changing regularly. So the question of which fractal is suitable for an antenna is still open. I really don't know. And why this one might be better than that one, I don't know that either. There should be a carpet in here. Yep, built in the manner of the Sierpinski carpet. So here's a Sierpinski carpet. And then there's also a Sierpinski sponge. Oh, and here's a little code for it. So probably I could find the Sierpinski sponge. Let's see if I can find that. Copy, select all, paste, Sierpinski sponge. There we go. Oh, they're calling that the Menger sponge, but it's really a Sierpinski sponge. That's how I know it. Oh, Menger sponge, okay. Oh, I need Java. So, that kind of looks like one of the Borg cubes. Is that a good antenna? A Sierpinski sponge? It wouldn't be easy to fabricate it on a in a printed circuit board, but I could build it in a 3D printer, but then it might not be conductive unless the 3D printer were printing in stainless steel. But there is one. There's one in Manhattan you can outsource your designs to, so it will print in stainless steel. So you could have a Sierpinski sponge in stainless steel if you like, or in ceramics even, although that might not help you. So there, you can print these things in any, well, you could, I don't think you'd want to mill that, but you could print these things in almost any form factor you like. It would be a very expensive project to have this printed in stainless steel. But how fun. So I have this this idea that you need to know more about fractals if you're going to do fractal antennas. And it's certainly okay to do fractal antennas for microcontrollers. I see nothing wrong with that. But this idea that
So what I was thinking is like the way how we transfer the power. I was trying to get a new
you're trying to do what now?
get a new idea of how to transfer the power.
Yeah, so has have they not done fractal antenna power transmission?
Yes.
They have. And so there's a couple of antennas for power. Here's one. Oh, and here's somebody who's used Sierpinski. I just saw that. Sierpinski microstrip patch for wireless power transmission. So if they're using Sierpinski, you might want to build a Sierpinski antenna too, but then maybe something else, something a little different. Yeah, maybe not a Sierpinski fractal, a different fractal, right? And you may find that if you compare it against the Sierpinski antenna, it works better. So clearly, there's a paper in that. If you told me, oh, I'm comparing the efficiency of 2 or 3 fractal antennas, and I'm building an experiment that lets me choose which antenna is better, that would be very interesting to me. Then I could say, great, let's publish that, and that becomes a good contribution. So did they tell you that they didn't use a Koch curve because Sierpinski is better? No, they just said, we're just going to do it, and here's our results. So why not say, great, let's take their results and try them with different antennas, the different fractals. In fact, I don't even know that he's compared this antenna against any other antenna. He just tried a few different iterations. So it's not clear. And it went into the International Journal of Computer Applications. I'm not sure if that's a good journal or not. I don't know that one. So this is a big question in my mind. Why use Sierpinski antennas? Why not use another one? Yeah, I mean, clearly we should be comparing antennas. There's a compelling argument that we need to know which is the best antenna. And there's no reason why we shouldn't be able to explore these things. Even if there is a patent on fractal antennas, we should at least know, in general, which ones are better. And if we can find one that is better, then there's an improvement patent that says... No, there's definitely patents on fractal antennas. Oh, with Witricity. Well, I don't know if you want to use the term Witricity. I think if you just use wireless power transmission, it's good enough. So let's think about this next homework assignment, because we're out of time. So in our last exciting readings assignment, I think we were up to homework number 8. So now what we're going to do is create a new assignment. And we'll call it homework number 9. And what shall we call it? Readings, literature, cited. And this will be due on the 26th at 12 and on and yes and yes and what else? Why is this like that? Okay. Let's see. Estimated time to completion 3 hours. Display grades on. What else? Okay. So let's see now. Create a PowerPoint that describes the contribution of, let's kick it up a notch, 15 papers. And let's make sure that these are journal papers. Okay. Not books. Not conference papers. Not technical reports. Not patents. Real live journal papers that you have read for the course. Each paper should take no more than one slide. Cite the paper. Paper. Lyon, 2005. George R. Well, it probably would be R. George or something. You know, you get the idea. Then list the papers. List the papers at the end of the presentation. Okay. Why is this in paper important to my work? How different is the prior work relative to yours? You still need to use that. Use journal. Journal, journal papers. Doing 1 week. 1 week. So presumably if you did it okay this week, you only need 5 papers for next week. But if you didn't do anything involving papers this week, now you need 15 papers. Wow. To order papers. Okay? Does everybody sort of understand the assignment? So don't just repeat like a presentation about what you're doing and why you're doing it. That, you know, don't like tell me about what sound is. Right? That's not what the assignment is about. Don't tell me what witricity is. But if you use a term like homopolar, I'm going to ask you what that means because maybe I don't know. So I will be able to tell if you actually understood what you were reading. Because if you were reading about homopolar but you didn't know what that was, or if you were reading about fractals but you don't know what a fractal is, then I can tell that you don't understand what you're reading. So show some evidence that you understand what you're reading. Don't just take a couple of paragraphs out of the paper and say, this is what it was about because here's the title. Next paper. That doesn't... Yep. So if you did it right this time, you only need 5 more papers. So yeah, let's try and see if we can keep up. Let's see. What do we got here? I think that's sufficient. Save. Oh, we got another assignment. So you guys are good. We've got an assignment coming up. Thanks very much. I'll stop my little presentation.